All right, here's 5-1, day 1. Switching gears a little bit in terms of function type, right? Really hit it hard in chapter 3 with polynomials, right? Where kind of the highest power, like you've got all these terms in the function, and the one that's the highest power kind of determines the characteristics of the graph. Exponential, take a look at it right here. Okay, different form, kind of looks a little bit similar, but a, which has to be a constant, is down in the base. Okay, that's a big difference, right? Now this list of powers, if you go across it, you keep the base the same, right? And you can kind of see there right off the bat why the base can't be 1, right? Because all these different properties that you'll see with exponential graphs, none of them happen if a is 1. It's just a horizontal line at y equals 1. So you do see in the definition, it's like, okay, a has got to be positive, right? We'll talk more about what happens with different values of a, but it can't be 1. It can be between 0 and 1, can be bigger than 1, but not 1, and you can see why. Now, as you go across, you see all these other different types of bases, right? The second row shows you, here's how fast the graph would, or the each term would increase if the base is 2, and then 3, and then 4. And I do want you to notice on this table that when you get down to like 10 and you go across, look at how fast everything increases, right? If you make that base really big, you get a curve that increases really quickly, okay? I'm going to jump over here for just a second, right? This piece with exponential graphs. We'll talk a lot more about this. They never change directions. That's where they are really different from polynomials, right? We saw that. We'd like find their zeros and see all these spots where they could change directions. That doesn't happen here. They're either entirely increasing or entirely decreasing. You're looking at an increasing graph if a is greater than 1, right? Which this whole table, right? You see as you go left to right, all the values are getting bigger because on all those, a is bigger than 1, okay? If you wanted to look at a decreasing graph, and throughout chapter 5, you'll see this a whole bunch, right? We'll see both. You'd have to look at a value of a between 0 and 1. So like point something. You don't see that here, right? So you're not, again, as you're moving left to right, you're not seeing any of these. When I say these numbers, right? Let me kind of clarify here. 10 squared is 100. 10 cubed is 1,000. 10 to the 4th is 10,000. 10 to the 5th, 100,000, right? If the number that was the base, in this case 10, was between 0 and 1, you would see those numbers get smaller as we make the power higher. But that's not happening because a is 10, not between 0 and 1, okay? A lot of algebra behind exponents. We'll work in that a little bit, right? Really 7 rules that once upon a time in Algebra 2, you saw these. These are not brand new algebra concepts, so I'm not going to spend a ton of time on them now, other than now that we've brought them back to just say, here they are, right? If we refer back to some of these rules of exponents, right, know that we might do that, okay? That might happen. All right, by the way, before we really dive into everything today, 5 is going to be a short unit, right? It's my plan at this point. We'll cover sections 1 and 2, right? If you were to look into your book, you'd see there's 5 total, and we'll still, maybe we'll go beyond 2, but my for sure plan at this point is we'll go into a lot of depth in section 1 and section 2, and then we'll kind of see from there as to what we'll do with 3, 4, and 5. Okay. A lot of times if you were to evaluate an exponential function, right? If you were to say, all right, I want f of negative 3.1 right? What you're talking about is 2 to the negative 3.1 power, okay? Something like that, you would probably need the assistance of a calculator, okay? That's, so whether you have a graphing calculator like a TI-84 or just a scientific, I'd spend some time looking at that. I can't tell you exactly where it is, but I know any basic calculator is going to do this for you, okay? Just know that. You would want to spend some time figuring out where those buttons are to take a base and raise it to a power. It's something throughout the chapter you're going to want to be able to do. It's going to make your life a lot easier. That's what you'd end up getting if you put that in, right? Kind of a weird thing here that, with a base of 2, you're probably expecting, hey, wait a minute. If you raise that to a power, we saw on that table, right, that if the base was 2, things get really big. But what you're seeing here is, you're raising it to a negative x value. So you end up with a really small y value. On the next one, if I didn't want to use a calculator, I really wouldn't. It's f of 3, which would mean I have 2 to the negative 3rd power, right? The negative sign is already up there. But if you went back to the slide before and you took a peek at your properties of exponents, or your exponent rules is what it says, you would find that if you got that negative exponent, right, this would still be f of 3. You could always do this. You could go 1 over 2 to the 3rd. You get 1 over 8, right? Had you just taken this and plugged it into your calculator, you would have just seen 0.125. And I'd be okay if you went either way, right? It's possible I could give you an expression to evaluate and say, hey, no calculator, you got to use the rules, but I don't think we're going to do that a ton. But I could. But I doubt it. All right, over on C, this would be another calculator one for sure, right? 0.6 to the 3/2 power. We would have a decreasing exponential curve. We haven't seen a picture of that yet. Actually, I haven't really talked about graphing at all. And in this lesson, we won't, by the way. We're not going to do any graphing. But that would be a exponential curve that is always going down. The y value, that is always going down as x goes up. Right? But that would be a tough one to evaluate, even with our exponent rules. There you go. Right, you get about 0.464. All right, do a little bit of a little algebra here. Not a ton, but I'm going to use it to do some solving. Okay, we're going to use what's called the one-to-one property. It's kind of a slick little way that you could use to solve some exponential equations. What it's all about is trying to get the base to match on each side, right? When you're dealing with terms that have exponents, if you can get bases to match, you got a good thing going, and the numbers work out pretty easy. Well, I shouldn't say easy. Easier than they would if we couldn't get the bases to match. Let's just say that. By the way, I hope you're not catching a lot of background noise here. You might be. I got my dog in the office here at home, and his name's Scout. He's old. He's almost 12, and he's napping in the corner, and he is out. He is sawing logs to the point where I'm curious if you guys can hear him. Hopefully he's not too distracting there. Rough life though, huh? Just find a spot anywhere in the house, any time of the day, just curl up and sleep. That's pretty much Scott's life. All right, back to it. Right here, this would be kind of an example of the one-to-one property. Over on this left side, I see 9, right? But I can write it to be 3 squared, so it would have the same base as the right side, right? Basically, when you do that, and you're like, on all of these, I'm going to solve, right? I'm working backwards to get A, right? If you were to do that, it's almost like the bases just cancel each other out. You don't have to worry about them, and you can just work with what's in the exponent. It's kind of nice, okay? That's what I was saying earlier, that if you can use the one-to-one to get your bases to match, it's a good thing, right? It's going to set you up that all of a sudden, it's almost like the fact that it's an exponential equation doesn't really matter anymore, right? Obviously, it would lead to a whole another question that what if it just mathematically wasn't possible to rearrange, or I should say to rewrite one side so that the bases were the same? What if you can't do that? It's another question for another day. If that's kind of the direction you were going, it's a really good thought. And it's one of those deals that would kind of come up in the second half of the chapter, I think, in learning targets 4 and 5. And again, we'll see where things go if that's something we'll get into. But that's kind of the stuff later on in the unit. For now, we're not going to go that route. All right, so I got 125 and 5, right? It's kind of similar to the first one, that my gut is, probably easier to deal with the bigger one, right? The bigger base, and specifically, can I write 125 base 5, right? And you can kind of go through a little guess and check, right? Obviously, you're not looking for 5 to the first power. What about 5 squared? What about 5 to the third? That's what you would kind of go through and check, right? And with the ones I would assign you, you're going to find, if you're checking the right base, you're going to find it pretty quick, right? You might check 5 squared, see that that's 25, and then you'd see 5 to the third is going to do the job, right? And one thing over here on the left, this is one of your rules of exponents, right? 5 to the third to the 2x power. That's a case where I can multiply the exponents, and I would get 5 to the 6x equals 5 to the 3x minus 2. And again, in terms of that equation, it kind of looks like a mess. But again, we rewrote it with this, using this one-to-one property, and we're like, all right, wait a minute here. How about 6x equals 3x minus 2, right? We've solved an equation like that from the first week of school, right? That's no big deal at all. Got a little bit of work left to do, but nothing terrible. Get to that. Divide by 3. And there you go, negative 2/3. One thing with solving exponential equations, again, to kind of contrast them from polynomials, because once we get to the graphing side, you will really see this is a different function family, right? The only way that I think you can kind of get them confused with polynomials is you have a base to a power, right? But again, the key difference is the x variable is up in the exponent, okay? But when you get to the graphic side, you'll see they don't look the same. But kind of on that note, when we were solving polynomials in chapter 3, which typically took the form of finding zeros, we could get a lot of answers, right? In fact, like the power that we had was kind of like how many we could get. That's not the case here, right? You should expect when you're solving to get 1, right? It would be, I want to say rare. The only thing that would make me say impossible is if there's just kind of some really weird example where you could get 2, but that's not going to come up. You should plan on getting 1 solution, okay? Kind of a tricky one here, right? The right side I like, base 2, right, which would tell me here, right, could I take 1/8 and somehow write that as base 2, okay? The fact that, I'm taking 2 to some power, right? The thing I'd be worried about here is you just go through kind of your guess and check, and you're like 1, 2, 3, 4, and you're like, I'm not even getting anything close to 1/8, which we saw on the other slide as a decimal is 0.125. Don't forget about checking negatives, right? That could come up too, and that's exactly what's going to happen here. Is 1/8 would be 2 to the negative third power, right? So when you're doing guess and check to get the bases the same, be aware of the negatives, right? You're not going to have to, again, with the ones I'll assign you, you're not going to have to check a ton of values. You could get to it pretty quick, but especially if you see that you're working on a fraction like 1/8, make sure you do that. We're back to our one-to-one property here. -3 equals x plus 5. Take away 5, take away 5. X would have to be -8. Other kind of just general observations here about solutions, right? I already pointed out, you should expect to get one solution. Should just get one. It could be negative, could be fractions, right? We're seeing that happening. As far as kind of the type of number that you get, again, fractions, decimals, negatives, those are all kind of in play. Don't be stunned if you see those. All right, tricky deal here, right? 216 and 36. This is probably the toughest one we've seen so far. What would happen is you did a little guess and check, is you'd see you don't have a lot of luck switching those bases to each other, okay? So you might have to change both, right? That's possible here. And again, if you were to, the key on this one would be to figure out that the base that you're going to want to look for is 6, which I think when you're looking at 36, you would see that pretty quick. 6 times 6 is 36, or 6 squared, which would give you a pretty good heads up that you'd want to switch this to base 6. And from there, I don't think it would be too terrible to find, because 216 is 6 to the third. 36 is 6 squared. Okay. Going back to that same exponential rule that we used over here, you would have 6 to the 12th and 6 to the 18x minus 4. That's exactly what we were looking for, because really all we have to solve is 12 equals 18x minus 4. Which looks like what we'd call just a nice equation, right? No square roots, no powers, right? The more kind of technical way to, I mean, you've probably seen that before, where you're like, hey, I just use my basic inverse operations and I work backwards. Typically in a functions course, when we see that going on, what's happening is you're solving an equation that's linear. So once we were able to cancel the 6's on all these, it's leaving us with a little linear equation to solve. Divide both sides by 18. I am going to get picky with you and simplify that because I can. 16 and 18 are both divisible by 2. So we would get 8 over 9. And there you have it. They're solving with the one-to-one property by getting the same base on each side.